Hello and welcome back again. So, we have been talking about this nucleation and growth mechanism as it happens in the process of atomization, and if you remember, this is what we talked about in the previous class as to how the nucleus of the solid forms and how it grows. Basically, it involves this free energy change as we have discussed with the help of this diagram which you see over here, right. Whenever there is a transformation like this, liquid to solid, or for that matter any transformation going from one particular state to another state, you need to look at the energy change from a thermodynamics perspective, whether that energy change is negative or positive, right. So, any transformation will occur spontaneously whenever this change of free energy is negative, right. So, that is what we have seen in this case as well, that whenever there is a transformation between liquid and solid, liquid goes to solid as the temperature is lowered below the melting point. This delta G becomes negative, because below the melting point, as you can see from here, the free energy of the solid, that is G s, is less than that of the liquid, which is G L, right. And as a result of that, delta G becomes negative, right. And as a result, the liquid transforms to solid. So, that is when the first particles of the solid forms, and these very small or tiny particles of the solid, the first few particles of the solid are known as the nuclei or the nucleus. The first particle of solid which forms is known as the nucleus. Okay. So, now depending on whether this nucleus is attaining a critical size or not, it will grow or dissolve back into the liquid. Okay. So, that is the growth criteria of this nucleus which forms, and this depends on these free energy terms, or these two contributions to the free energy change. One is the volume free energy change delta G V, and another is the surface free energy, right. So, from this we could derive the critical size R star which is given by this gamma and delta G V, right. And only when this size reaches this critical size, the size of the nucleus, when it reaches the critical size R star, then only it can become stable and grow further. Okay. So, now in today's class we are going to see as to what is that criteria for the growth of this nucleus and how the solid ultimately grows. Okay. So, if you look at this crystal growth from liquid, it is basically the growth of that nucleus which forms and then attains the critical size, right. So, when that happens, then there is an interface which develops between the liquid and the solid which is growing. Okay. And how this solid will grow, that would depend on how atoms are coming from the liquid and joining the solid. So, there is a movement of atoms from the liquid phase to the solid phase for the solid to grow, and when the solid cannot grow, that means when we are talking about a scenario where it is still in the process of attaining the critical size, then it can dissolve back into the solid, and then there are movement of atoms from the solid to the liquid, right. So, you can see here that across the interface there is two way movement of atoms, okay, either from liquid to the solid or from solid to the liquid, right. So, from an energy perspective, if you see this for the solid to grow, there is a energy barrier to it, or there is an activation energy which is needed for the solid to grow from the liquid phase. Okay. Let us say this y axis is internal energy, and this is where our interface is, the right of which is liquid and at left you have solid. So, the energy is plotted as a function of distance from the interface. So, as I said, when you look at it from an energy perspective, there is an energy barrier. Okay. So, that can be represented with a plot like this. Okay. So, if you see for the solid to grow, or for the atoms to transfer from the liquid to the solid, this energy barrier which is given by this distance between this well and this peak over here, that has to be overcome. Okay. Similarly, from the movement of atoms in the other direction, this is the energy barrier that has to be overcome, right, because the growth of the solid is dependent on the attachment of atoms from the liquid phase, right. As I said, the atoms have to move from the liquid and go to the solid and attach to it for the solid to grow. So, that rate of attachment, if you write, that can be written as this. right, where Rf0 is a constant which basically is related to how these atoms which are coming from the liquid to the solid, how those atoms are being accommodated in the sites inside the solid. Okay. So, that accommodation or the ease of these atoms to be attached to the solid, that is given by Rf0, and that is why this is also known as an accommodation factor. And Qf is the activation energy, as I said, which we can see from here, and the other two terms have their usual meaning, that is R is the gas constant and T is the absolute temperature. And similarly, for the solid to get dissolved back into the liquid, there has to be detachment of atoms from the solid and going into the liquid, right. So, that rate of detachment can also be given by a similar relationship, like how the rate of attachment is given. Okay, so, there is an activation energy which is required for the solid to grow, and the difference between these 2 points, that means these 2 potential wells that you have, the potential well for the liquid and the potential well for the solid, the difference between those 2, that means this difference, this is obviously the latent heat of freezing. Right, because here we are talking about freezing of a solid, that means solidification from the liquid phase. Okay. Right. So, once this activation barrier is overcome, more and more atoms will attach to the solid. So, this this rate of attachment that you see over here, that is going to increase as more and more atoms attach to the solid and it grows. And as a result of that growth, this interface is also going to attain a particular growth velocity, because the interface is also going to move when the solid grows. That interface will move towards the liquid, so that the solid will grow more and more, right. So, once this happens, there will be a growth velocity which can be assigned to the interface as well. Okay. So, this is how from a thermodynamic point of view, you can see how the solid will grow from the liquid phase. Okay. And from here, when we come back to the process that we were talking about so far, the process of atomization, that is what our topic is right now. Okay. Now, if you come back to this, here you are actually forming these solid powders from a stream of liquid metal, and that is how this nucleation and growth aspect is coming into picture over here, right. So, here you can see the powder is forming from the liquid phase, and considering this thermodynamics, we saw that how or what is the criteria for the solid to crystallize or for the solid to form from the liquid phase. Now, if you also want to know as to what is going to be the structure of this powder which is forming from the liquid phase, then you will also have to consider the kinetics aspect of this solidification process. That means, you will have to see what is the rate of nucleation and at what rate it grows. That will decide the structure of the solid which is forming in terms of whether it will be a finer or a coarser particle, or whether the microstructure, as we call it. Microstructure is nothing but the internal structure of any material, whether the microstructure is going to be fine or coarse, that would depend on the kinetics of the process. Okay. So, let us try and understand that as well, because ultimately we will have to correlate the process to the structure that we get inside a material, including these powders, right. And that is what we call as structure property correlation, because the structure will finally decide the properties. And as you would have seen in the beginning few lectures, that we had also talked about the correlation between the processing and the structure, right. So, how the processing aspects are like this thermodynamics and kinetics, right, that would decide the structure of the material, for example, this microstructure, and this in turn will decide the properties of the material. Okay. Okay, so, let us see what are the kinetics aspect of this atomization process or the solidification that happens in atomization, right. So, as we understood by now, once the embryo reaches that critical size R star, the growth process will start. And on the other hand, nucleation continues simultaneously. That means, once this critical size nucleus starts to grow, more and more smaller nuclei will also form simultaneously, and as in when this nuclei also attain that critical size, they will also start to grow. Okay. Now, depending on what is this rate of nucleation and what is the rate of growth, depending on that your microstructure will be decided. So, whether you would get a finer grain size, that means a finer microstructure or not, that is going to be decided by the nucleation and the growth rate. okay, or the competition between this nucleation and growth rate. Okay. And here you should also understand another parameter known as undercooling, because what happens when you solidify a, a solid from the liquid phase, the liquid has to be cooled below the melting point. Okay. Then only this solid uh, will grow continuously, and ultimately all the liquid will transform into the solid phase, right. So, this cooling below the melting point without starting the nucleation of the solid crystal is what is known as the undercooling, right, which is given by this, this T, for example, is the temperature to which the liquid is cooled below the melting point when it is still in liquid condition. That means the formation of solid is yet to start, but the temperature is still below the melting point. Okay. So, that undercooling or Tm minus T or this delta T, that is what is needed for the solidification process to start. Okay. And this free energy change, the volume free energy change delta G is a function of this undercooling, as you can see from here, where delta G naught is the standard free energy change. And therefore, you can see what will be the effect of the undercooling from this simple equation itself. Okay. So, as delta T or undercooling increases, delta GV would also increase, and from this relationship you can see that as delta GV increases, it becomes easier to form more and more nucleus, right, because the critical size needed for the nucleus to be stable decreases, and the critical free energy change also decreases, right. So, as delta GB increases, it becomes easier for more of these solid particles or more of this nucleus of the solid phase to form. Okay. And as a result, you can expect the nucleation rate to increase as the undercooling increases. Okay. So, delta T will then equate proportionately to the nucleation rate. Okay. As delta T increases, the nucleation rate will also increase. And if that happens, if the nucleation rate overtakes the growth rate, that means if the nucleation rate is higher than the growth rate, then the microstructure is going to be finer, right. Because in that case, as the nucleation rate is higher, you can expect more and more nucleus to form in a given period of time, and therefore, the growth is or the rate of growth will be much lower compared to the nucleation rate. And on the other hand, as I said, there will be more number of nucleus also. Okay. So, these two factors, that means the formation of more number of nuclei in a given period of time and less growth will ensure that the microstructure does not grow. Microstructure can be characterized by different aspects or by different kind of features. Grain size is one of them. So, that will lead to the finer microstructure or finer grain size. Okay. You can also say that a high nucleation rate in the case of the atomization process would also lead to finer particles. Okay. That can be seen over here. The nucleation rate is given as a function of temperature. This is the nucleation rate and this is the growth rate, and overall transformation rate is just the sum of these two. Okay. And as I said, this microstructure would depend on which is prevailing over the other, whether nucleation rate is prevailing over the growth rate, and in that case you are going to end up with a finer microstructure. And on the other hand, if the growth rate prevails over the nucleation rate, that means if the growth of these nuclei which form is high, then you can also expect these grains to grow, right, if you talk about the grain size. And as a result, the size of the grains will be high, what is known as a what can be called as a coarse grained microstructure or a coarse microstructure, right. And that in turn, as I said before, is going to depend on this undercooling. Right. So, this is how, as I mentioned before also, this is how the kinetics of the nucleation process which relates to nucleation rate would decide the microstructure, whether it is going to be a fine or a coarse kind of microstructure. Okay. Right. So, that will give us an opportunity of controlling the microstructure in the atomization process. And this is an important aspect because, as I said, the properties that we are going to get from a powder, or for that matter for any material, that is going to depend on this microstructure, right. So, how that will be controlled, that is what will be our next topic, or that is what we are going to discuss next. So, with this I am going to end today's class, and I will see you again in the next class. Till then, goodbye.